This graph is going to help you identify some this video is going to help you identify some important features on graphs. The things we're going to talk about is identifying the labels for the axes of the graph and the units of the things that are being graphed, the zeros, the maxima and minima, the slope, and then identifying the relationship between the variables. These are the main things that I want you to be able to identify when you're looking at a graph. So this is an example here. This picture shows you a function that is being graphed. So on the y-axis, I see that the account balance is the physical quantity that's being graphed. And on the x-axis, I see time is the physical quantity. So this is a function that shows the amount of money I have in units of US dollars as a function of time in units of days. You can notice just by kind of looking here some features of the graph. You can see that there are some peaks and valleys within the graph. So this location right here is called a maxima. Over here I'd see another maxima. You might refer to these as local maximum because they have, obviously one of them is higher than the other one, but within that neighborhood or that locality, that is where the function has its highest value. So a graph can have multiple maxima. We just refer to them as local maximum. Same thing with minimas. This particular graph has one local minima. If it really only has one minima, you could call it the global minima. Other things you want to look for on a graph is where the graph crosses the axes. Where the graph crosses the x-axis is given a special name. It's called the zeros or the roots of the function. These can be very useful in identifying different values on the graph. But where it's crossing the x-axis, the function has a 0 value for the y-axis. So that's why it's called the zeros. These are important features you might need when you're solving a problem. Being able to identify, when I say the word zeros or roots is another name, that's literally where the graph is crossing the x-axis. So these are some important things you always want to identify when you're looking at a graph. Another really important thing to talk about when you're looking at a graph is describing the slope of the graph. You only can calculate the slope of a line. So on a graph like the one that I was just showing you, you can describe the slope, but you can't necessarily calculate it because it's changing at all different points. On a line though, the slope stays the same. So for an example here, here's a line. No matter where you choose 2 points on the line, maybe this point and this point, you'll always calculate the same slope. If I chose this point and this point, I'm always going to get the same slope because a line has a constant slope. The way to calculate the slope is to choose 2 points. You find the change in the y values divided by the change in the x values. Therefore, slope has units of whatever is being graphed on the y-axis divided by the units of whatever is being graphed on the x-axis. So every graph has, the units of the slope will be different depending on what's being graphed. So a line has a constant slope. So a graph that has constant slope should look like a line. It will have one slope. A graph that has 0 slope is the special case. It's a horizontal line. It's not going upwards or downwards. It's just perfectly horizontal. It has 0 slope. More often than not, though, your graphs are going to have changing slope. They're going to be getting steeper in certain areas and then getting more shallow. Maybe they have a maximum or a minimum. That implies that the slope is changing. It has some kind of curvature to it. So whenever your graph has curvature, you need to describe the slope in a slightly different way. Let's do a couple of examples here. I want you to try to finish these off. I'll do a few of them for you. See if you could sketch a graph that has the slope described by these phrases here. So I'll do one of them for you. How about negative constant slope? If you see that word constant, that should imply to you that I need to be drawing a line. A line has constant slope. Negative slope means that the line is sloping downwards. So there's an example of negative constant slope. Let's try a tougher one. Whenever the slope is not constant, it makes it a little bit tougher. If it's not constant, if it's increasing or decreasing, that implies that the graph has curvature to it. Let's try this one. Positive increasing slope. So the slope needs to be getting steeper and steeper and steeper, and my graph needs to be sloping upwards the entire time. So this graph that I've just drawn, you can see that it's kind of flat at the beginning, And then as it keeps on going, it's getting steeper and steeper and steeper. And the slope itself, the graph itself, it's always sloping upwards. So there's an example of positive increasing slope. I'll do one other one for you. Let's do positive but decreasing slope. So I need to start off steep and then get shallower and shallower and shallower, but always still kind of going uphill. I'm still sloping upwards. So this is a good chance for you to pause the video and see if you can do the other three that I didn't do for you. See if you can draw those three graphs. If you want to actually describe the slope of a graph that's nonlinear, the best you can do is something called instantaneous slope. What that means is that when a graph has curvature to it, the slope is changing constantly, which means you only can describe the slope at one instant in time. So what you want to do is identify what instant you want to describe the slope at, and then draw a tangent line at that instant. So let's do an example where, let's say that I am interested in what the slope of this graph is at the instant in time when the x value is 8 seconds. Draw a tangent line at 8 seconds. That means that you're going to draw a line that touches your graph at exactly that location, 8 seconds, does not intersect the graph, it just kind of grazes it and keeps on going. So this tangent line that I've drawn, it touches the graph right about there at 8 seconds. And what I can do now is describe the slope of that line. So all I need to do is identify 2 points on that line. Doesn't matter what 2 points at all. I'm going to go with that point there at 8 seconds. So that's 8 seconds and about maybe negative $167. That's 1 point. Another point that I could do, I think this one looks pretty good. 6 seconds and about negative $75. Now I have 2 points and I can calculate the slope of that that tangent line. That tells me the slope of my graph at that instant only. If you found it at different locations on that graph, you would see that the slope is changing. Identify, I can see on this graph right here, I can see that the slope is getting steeper and steeper and steeper. When you do this process, you're not going to necessarily get the exact, like, perfect answer. You would need calculus or computer to get the perfect answer. So if you're comparing your answer to mine sometimes, or to maybe to a peer, you might get slightly different numbers, but they should be pretty close to each other if you're being very careful about drawing your tangent line. The last thing I want to talk about is describing the relationship between variables that are being graphed. We typically put the independent variable on the x-axis and the dependent variable on the y-axis. This implies that the x-axis is going to change, and we want to see how the y-axis is changing because of that. So the y-axis is the thing that is dependent. We're seeing how it depends on the thing that's being graphed on the x-axis. So you really want to ask yourself, as this x-axis is changing, how is the y-axis changing in response to that? Here are some examples of typical relationships between variables. These are the ones that I definitely want you to know. There are many others that exist, but these are probably the most important ones, or the most common ones that you'll see. This first one right here, independent, that means that the y-axis does not depend on whatever is being graphed on the x-axis. Notice that the y value is staying the same even though the x value is getting bigger. So the x value is getting bigger to the right, but y is staying the same. Some other important ones that you might notice here, and you'll kind of notice some similarities between certain graphs. Commonly students will confuse the quadratic graphs and the exponential graphs. It kind of just depends on what section of the graph you're looking at, because they really can look very similar. What's important though that I'll note for you right now is that an exponential graph, it's using the exponential function, and whatever is being graphed on the x-axis is actually in the exponent. That's what makes it different between a quadratic graph, where y is maybe just x squared. So the exponent in a quadratic graph, the exponent is the number 2 or 4, anything like that. But for an exponential graph, the x value is actually in the exponent itself. And so there's actually a lot steeper growth typically in an exponential function. But I would like you to know these particular, what these graphs look like, these relationships. and be able to describe, if you looked at a graph, try to identify features that might lead you to believe that one of these functions or one of these relationships is true. I put descriptions, further descriptions for what these things look like, and even some possible equations to describe them on this tutorial page. And so you should definitely take a look down there and familiarize yourself with all these types of relationships.